This is Dr. Rahil, and we are going to start chapter 8, Deadlocks. Before that, we have studied several synchronization tools which were there to avoid the deadlocks. However, the deadlocks itself, the topic was remaining. So in this chapter we will be covering the deadlocks, and this is the chapter 8 in the series of operating system course. So outline of the course, we'll see first the system models. In system models we'll see that what are the components of a of the system and how these components are represented inside the system. The components representation, inside the system. Okay, and then we will see the Deadlock characterizations. Actually, there are 4 main criteria which are evaluated to see if there is a deadlock or not. Okay, so we'll see the 4 criteria. The main criteria, also known as characterizations, that represents the occurrence of a deadlock. Okay, that may give us a signal that the deadlock has occurred. Okay, if these 4 criteria are met, then we can say that there is a deadlock. And then we will see that how many methods are there to handle with the deadlock. So the first one is deadlock prevention, and that how we can prevent a deadlock has already if the deadlock is going to occur. And the second one is that we shall avoid the deadlock before before letting the processes to go in the CPU or the system for processing. So there are these two approaches are very main approaches, and then the third approach is deadlock detection and deadlock recovery. Also there is a fourth approach which is not mentioned here, but the fourth approach is that deadlock ignorance. Okay, deadlock ignorance. Okay, ignore that there is a deadlock and let it go. So this is the most common approach which is being used by many operating systems. So we can say that this is an important topic, but as we shall understand that how deadlocks can be prevented, because there are many systems which are real-time systems, and they must be implementing some priorities and different set of scheduling algorithms. So the deadlock topic itself is very important, but if we see the existing operating systems we use at the user level, this is of less importance, because many companies like Microsoft, like Linux, really ignore the existence of deadlock. Okay, and many more operating systems ignore the existence of deadlock and pretend that it is not there, because the frequency of occurrence of deadlock is very rare, is very low. Okay, the frequency of occurrence of a deadlock is very low. So this is the outline of course, and the chapter objectives, and then come to the system model. Now in every system, the system resource types such as CPU cycle, memory space, and IO devices, or any hardware or software resources, are represented we can say represented as the resources of the system. So for example, if we say that R1, this is R1, this is R2, and this is maybe RM. So the resources are represented as we can say that in this chapter I'll be representing resources like this with R. Okay, and R1, R2, up to RM are the resources such as CPU cycle, memory space, and IO devices, and etc. Right? So these are the resources of the system. Okay. Now each resource has some associated instances. For example, if we are accessing the memory, then there might be multiple instances of the memory. Okay. If we are accessing the CPU cycle, then there might be multiple instances of the CPU cycle. And if we are accessing the IO devices, any of IO devices, then there might be multiple instances of IO devices. For example, if there are printers connected, maybe 5 printers connected, or maybe 3 printers connected, then there would be multiple instances of this device. Okay, IO device. For example, if this is an IO device, and for example, if memory, then we can say that if there are 2 instances, and for CPU cycle, we just assume that there is 1 instances. So every resource has is associated with some number of instances, and these instances can be utilized by any process concurrently. For example, if there are 3 printers, then 3 different processes can access this printer, but not the 4. For example, if there are maybe 4 printing jobs in the queue, okay, if we say 1, 2, 3 and 4 and maybe 5, right, 5 printing jobs in the system, then 3 of them would be allocated with a printer, right? Maybe printer 1, right? Let's say this is printer, and this is printer 2, and this is printer 3. Okay, so we can say that 1, 2 and 3. Now these 3 instances will access the existing resource, right? While remaining 2 instances will be waiting for the release of the resource, right? Waiting for release of the resource. Okay, so so we can say that a system process utilizes a resource as follows. First, it requests a resource. When it is allocated, it uses the resource, and once the thread or a process complete its execution, then it releases the resource. So we can say that if this is a process P1 maybe, okay, and there might be 1 instance, and it is performing some job of maybe printing, okay, or maybe anything, right? Any job, any existing hardware, right? So we have only 1 instance of this existing hardware, right? Hardware or anything, right? So what will happen? This cycle actually works like that. That first it requests the resource. Okay. When the resource is assigned, actually this resource is being assigned. Now this is connected with, we can say this is connected, right? This is to be communicated. Okay, so the resource is assigned to P1, right? Once it is assigned, this uses the resource, okay, and when the job is completed, at the completion, the resource is released, right? So we can say that this dash line is deleted and this request line is also deleted. Okay, so we can say that a system a system process utilizes a resource using this process cycle, right? So request, use, and then release. Okay, so a deadlock with a semaphore can occur. For example, as I have already given you an example, that if there is one train, right, there is one train and it is coming from maybe this way, right, and there is another train let's say my drawing might be very good, but for explanation there's a train, right? This is also I'm trying to draw for you guys. So these two trains are moving, right, on a same track, right? But at some time, right, there might be a way, go here and go here, right? But for some reason these two stop here and keep on waiting for resources, right? Maybe S1, this is waiting for S2, right? So this wants to move here and this wants to move here, but they are waiting, right? They are waiting for this to perform. For example, this one, the train 2 is waiting for train 1 to go first, and the train 1 is waiting for train 2 to go first. So these processes are actually in a semaphore, right? In a circle, in a way that they cannot proceed with their execution and waiting for someone else, and this wait goes to indefinite, right? Infinite. This wait is infinite. Okay, so that's why in this condition we can say that there is a deadlock. Okay, so there are several characterization, and there are 4 characterization of the deadlock, that how we can identify if the deadlock has occurred. Okay, so let me put my a little bit below, right? So the first one is mutual exclusion. Now these 4 conditions should meet. If one of these conditions is not met, then there is no deadlock. Okay, so we can say that deadlock can arise if 4 conditions hold simultaneously. If these 4 conditions occur simultaneously, then only we can say that there is a deadlock. A deadlock, or maybe the possibility of deadlock. Okay, so otherwise there is no deadlock. So the first one is mutual exclusion. Only one process at a time can use a resource. This is what we have studied in previous chapter, that if there is only one resource, as I have already told you, this is resource 1 and it has only one instance, right? This is the condition of mutual exclusion, right? That if 2 or more processes are trying to access this resource, in such condition, this condition in a deadlock, this condition is necessary. Okay, number 1. And number 2 is if there is a mutual exclusion. Now we are actually this is a checklist. Okay, consider this is a checklist. If this is the condition, then there is a possibility of deadlock. Now the second condition is that hold and wait. Now for suppose that P1 and P2, P1 and P2, right? This is, let's say, R1 and this is R2. Now P1 is having access to R2, P2 has access to R2, while P1 is requesting R2, right? P1 has P2 has access to R2, right? P2 is assigned to R2 is assigned to P2, while P1 is requesting the R1, right? And R1, wherever the R1 is assigned to P1 and is requested by P2. Okay, now in such situation, when this P1 is waiting, is having a resource R1, but it's still waiting for a release of resource of R2 from P2. Now and similarly the P2 is having the resource R2 and waiting for resource R1. Now in such condition, this condition is known as hold and wait. Now in this condition there is also a possibility of deadlock. So in situation we know that there is mutual exclusion because the instance of resource is only one, and these two processes are waiting for each other, and while keeping some of the resources engaged with them while they are waiting. So these two conditions are met. Now let's proceed with the third condition, no preemption. For example, if this P1 is non-interruptible, no preemption means non-interruptible, means this process cannot be splitted or cannot be divided into multiple tasks, right? This is the whole process. It should be executed atomically. Okay, so in such condition, if P1 and P2 both are the processes with no preemption, they cannot be they should be executed at whole, right? Atomic execution. So we see that this condition is also occurred. The fourth one condition, very important condition, is that there exists a set of P0 to Pn of waiting process, that P0 is waiting for a resources that is held by P1 and P1 is waiting for resources that is held by P2 and this is going to happen, and everyone is waiting for someone else is waiting for resources that held by Pn, right? So similarly we can say that processes are waiting for each other in a circular way, right? So we can say that there is a cycle also. We can say that there is a circle also, that every process is waiting for the release of resources from other process. For example, P1 is waiting for P2, right? P2 is waiting for maybe P3, and P3 is waiting for P4, and P4 is waiting for P1, right? So now in such condition we can say that this is a circular wait and it will never end, right? Infinite wait. As I have already told you, this is an infinite wait, and in circular interest, in circular if the circular wait, this will not never end. So in this example we have seen the four conditions, and four conditions are met. Then we can only say if these four conditions 1, 2, 3 and 4 up to 4 conditions, if these all are met, then only we can say that there is a deadlock. Okay. So whenever we are evaluating some algorithms, whenever we are studying some algorithms, or whenever we are implementing some algorithms, the deadlock avoidance should be cleverly designed to meet to check these conditions first. If these conditions are met, then we can say that there is a deadlock. Okay, otherwise there is no deadlock. Now, and another thing is a resource allocation graph, how these deadlocks can be represented. Now in previous slides I have shown you some representation where I was representing resources with a square, and I was representing the processes with some circular, right, circle. And similarly the requesting edge was also, I have already shown you, but it was not formally told you, that for example if P1 wants a resource from R1, right, now this will request, right, this will request. Now this edge is request. Now first I tell you that process is represented with this circular symbol, and the resource is requested with this rectangle or whatever the square, right, square symbol, and the edges, another thing is edges, that request edge and the assignment edge are represented with the arrows. Now this arrow from process to resource is requesting edge, and from resource to process is actually assignment edge. While this is request edge. Okay, so this is request edge, where from process to resource an arrow goes, and from resource to process is the assignment edge. This is actually when you are requesting a process, and when the when you are requesting a resource, and when the resource is assigned to you, right? And there is also something else, we call it as instances. I have already shown you that if this is the resource 1 and it has maybe 2 instances, now these instances are represented with this dot, right, dot symbol. Single dot means single resource, double dot means double resource. If we have 4 resources, we can represent like that. If we have 5 resources, we will add 1 more. Okay. So these are the instances of a resource. Now here an example of the resource allocation graph, and one resource R1 has 1 resource, R2 has 2 resource, R2 has 2 resource, R1 has 1 resource. Okay, one instance of R3, right, R3 have also 1 instance, and 3 instances of R4 and 3 instances of R4, right. T1 holds the instances of R2. T1 actually represents the thread. Now this can be a thread, this can be a process, right. While I'm going through this chapter, I'll be using these words interchangeably, but remember that this can be a thread, this can be a process also. Okay, so this applies to both. This definition, this resource allocation graph, whatever the techniques I tell you, applies to both the process and the resource. So T1 hold one instance of R2, right, one instance of R2, and waiting for an instance of R1, right. This is assignment, this is a request edge, right, and this is an assignment edge. This is a request edge. Okay, this is an assignment edge, and this is a request edge. Now as we can see that this R2 has 2 instances, so we can say that there might be no deadlock there. There might be no deadlock. Okay, well, there is actually no deadlock. Now we will see a condition where a deadlock actually exists. Now for suppose here is a graph, resource allocation graph, and we will see evaluate this graph if there is deadlock or not. Now we see that T1 requesting, this is a request edge, oh sorry, this is a request edge, right, this is an assignment edge, okay, and this is also an assignment edge, and this is a request edge, and this is an request edge, right, this is an assignment edge, and this is a request edge, right. So now we'll see that this circle has no deadlock because there are plenty of resources to fulfill this need, right. But if T3 is also requesting the resources, then we can see that R2, R3 and T2 and T3 are forming a cycle, right. right? These two are forming a cycle which can fall into the deadlock. The deadlock can be there, right? Can be there, right? Now because this T1 is waiting for some resources to be released by R1, while T2 is waiting for some resources to be released by by T3, and T3 is waiting for some resources to be released by T2 or T1. So we can say that these three are actually critical components of this process to and forming some deadlock, possibility of some deadlock. Okay, there might be some a deadlock, because if only if these all only if these all are non-preemptible. Right, this is also condition. So number one condition, there is a mutual exclusion. Yes, there is a mutual exclusion, and mutual exclusion also exists here, and hold and wait also exists there, right? Because everybody is waiting for everybody else, right? So hold and wait is also exists. Number one, mutual existence is there. Number two, hold and wait is also there. Number three is what was the number third? So number three is no preemption, right? Number three is no preemption, and number four is circular wait. So all our conditions are met here, so we can say that this condition is with possibility of occurrence of deadlock.